for a spring mass system with no damping, given a base excitation of this form, and given the natural frequency, we are asked to determine what is the maximum relative displacement of this system. So let's define first the relative displacement. So we have a system moving over a base, which at the same time has a movement. So the relative displacement we can define by parameter theta being equal to x minus y, which in other words means the system movement minus the base movement. If we can substitute this parameter theta in the differential equation, we're going to have theta double dot plus 2 damping ratio Wn theta dot plus Wn squared theta equals minus y double dot, or the negative of the acceleration. Now, let's then start by finding y double dot. So we're giving y dot, we're giving the velocity of the base excitation, and let's rewrite this equation of velocity as something like this. And now let's take the derivative of the velocity, which is going to be the derivative of this, the delta function, minus 100. Now let's take the negative of that function, because we need the negative to substitute in our previous equation here. So negative acceleration is equal to minus 20 delta function plus 100. And that is the value that we're going to use in this equation. Okay, now let's substitute this in the previous equation where we have theta double dot plus 2 damping ratio Wn theta dot plus Wn squared theta equals minus 20 delta function plus 100. Now we want to take the Laplace of this function, so we can get in a form of Laplace, and then taking the inverse of that function is going to give us the equation for the displacement or relative displacement theta in terms of time. So let's do that. Let's find what is the Laplace, but before we do that, we need to recognize that theta dot, this part of the equation goes to 0 because there's no damping. So damping equals 0. So the equation becomes more simple. Let me write it down here. It would be plus Wn squared theta equals minus 20 delta function plus 100. Now taking the Laplace, we know that square theta ds plus Wn squared theta s equals minus 20. Recognize that the Laplace of the delta function equals 1 plus the Laplace of a constant 1 over s. Note Laplace of delta function equals 1. Now let's rearrange this equation, and we're going to get theta s squared plus Wn squared equals minus 20 plus 100 over s. Rearranging this equation even further, we have theta s equals minus 20 over s squared plus Wn squared plus 100 over s squared plus Wn squared. Now let's we need to find out the inverse Laplace of this function so we can get the function of displacement with time, or theta t. Let's look at the first term. If we go to the Laplace tables, we notice that a, if we use parameter a, so a over s squared plus a squared gives me the sine of at. So I'm going to rearrange this so I can have the same format that I need for Laplace. So for that, I'm going to take negative 20 outside, I'm going to divide this equation by 10, and I'm going to also arrange this. So I'm going to have s squared plus wn squared over 10. And so 10 is A, and Wn is given the frequency is 10, so 10 squared, and then I have 10 here. This is the sign of this function. So from here, the inverse of this function is going to be equal to, I'm going to write here theta t is the inverse of this function, right? The inverse of this function is going to be equal to minus 20 over 10 sine Wn(t). Now, let's do the same for 100 plus the inverse of. Notice that from the Laplace tables also 1 over s multiplied by s squared plus Wn(t) or at is equal to 1 over a squared multiplied by 1 minus cosine Wt. So I'm going to use the same thing. I'm just going to get this 100 over here. And I have 1 over s squared plus Wn(t). And we know that this is going to be, I'm sorry, this is a square here, so square here. This format gives us, the inverse of this format gives us something like this. It will be 100 over Wn squared multiplied by 1 minus cosine Wn(t) from Laplace tables. So now we have the inverse of this function. And now we're asked to have the maximum displacement. So the maximum displacement of a function occurs when we derive this function and we equal the derivative to 0, because that will be a point of inflection. So we want to take the derivative of this function equal to 0 to get the maximum displacement. So let's do that. First, let's identify these like minus 20 over Wn, because 10 is Wn, sine Wn(t) plus 100 Wn squared, 1 minus cosine Wn(t). If I take the derivative of this function, I'm going to have theta dot, and theta dot is going to be equal to the derivative of the first term, which is going to be minus 20 multiplied by Wn over Wn cosine Wn(t) plus 100 Wn squared per Wn sine Wn(t). The derivative of this constant is 0. The derivative of this is going to be Wn sine Wn(t), the negative of it, multiplied by the constant. Okay, now we have theta dot. If we equal theta dot to 0 to get the maximum displacement information, we can have this form, minus 20 cosine Wt equals 100. So this will be positive because I'm going to pass this to this side. Wn squared by Wn sine Wn(t). Now let's take the tangent of this. So I get 20 equals, divided by, if I divide this equation in both sides by the cosine of Wn(t), I'm going to get 20 equals to 100 over Wn tangent Wn(t). And let's find the tangent. So the tangent of Wn(t) is going to be equal to 20 over 100 by Wn. 20 over 100, so it's the same time it's going to be equal tangent Wn(t) is equal to 1/5 Wn. Okay, let's just put this equation here. And so if the tangent, if we make a small triangle here, we can see that W and T, the tangent, then it has to be something like here is here. So this part is going to be identified like that, the Pythagorean term. So we just say that we have these, we have identified these values. We can find, in the same manner, cosine W and T is equal to 5/25 plus Wn squared, which is cosine of this is equal to the adjacent over the hypotenuse. The same time, sine Wt is equal to Wn over the square root of 25 plus Wn squared. Now, we have identified cosine and sine and tangent. We can now substitute in our equation for theta versus time, which is this equation. We can substitute here sine, the value of sine. We can substitute in this equation the value of cosine to get the function for the maximum relative displacement. So let's do that in here. So now theta max is going to be equal to minus 20 over Wn, the sine, which is Wn over the square root of 25 plus Wn squared, plus 100 Wn squared, 1 minus cosine, and the cosine is equal to 5 over square root 25 plus Wn squared. So now we have identified the equation of motion, the maximum relative displacement of the system by replacing the values of sine and cosine in the following equation.